Oh, you want to show something? Just to read out.
Konnichiwa to everybody. The later you come, the more up front you have to sit. So there are still a few seats. This one is reserved. Two more here.
One there.
One there. In any case, it's a good sign.
Yeah,
it's a good sign. It's a good sign for both of us, I would say. So welcome to the inaugural Presidential Lecture Series. This is supposed to be the first of many exciting talks to follow in that series. As we all know, science and technology are the key ingredients that drive our future. And indeed, we live in an extraordinary age where information and technologies are generated at a pace never seen before. And let me share just one number with you. In a few years, the total amount of new information generated on our globe will double every 12 hours. So we have a hell of a lot of things to learn. But how can we make sense of that incredible mass of information? How can we differentiate the important from the unimportant? Well, we need filters. The best filter is, of course, the people who work at the cutting edge of science that can explain to us what their findings actually mean. Among those, however, there are only a select few that can present it in a way that is easy to understand. The presidential lecture will provide you with a forum for those in order for all of us to learn what the future holds in stock for you. Throughout my lifetime, I've experienced a great number of speakers, and it was a great fortune, actually, to learn from these speakers, to learn about the excitement of science, about new findings. And I wanted to share that experience with you. So my hope is that you will leave here today more inspired to pursue your own research, more encouraged to come back next time to learn about science, and more committed to support the vision and mission of OIST. Today I'm very honored to have Professor Hitoshi Murayama here with us to begin this particular series. Hitoshi received his Ph.D. in theoretical physics from the University of Tokyo in 1991 and has been a faculty member at the University of California in Berkeley since 1995. Since 2007, he has also been a director at the Kavli Institute for the Physics and Mathematics of the Universe of the University of Tokyo. He received the 2002 Yukawa Commemoration Prize, and in 2017, just this last year, but I'm coming to the point, Alexander von Humboldt Foundation Research Award that comes with some interesting issues like shaking the hands of the President of the Federal Republic of Germany last week.
Hence presidential, yeah.
He is a fellow of the American Physical Society and a member of the American Academy of Arts and Sciences, as well as the Science Council of Japan. Not only is Hitoshi a renowned theoretical physicist, but he has also been a good friend for OIST for many years, from participating in an OIST colloquium in Tokyo in 2013 to giving the keynote lecture at the OIST Forum in Tokyo in 2016. Hitoshi has shown over and over again in TV shows, newspapers, books, and on radio that it is possible to explain complex matters in simple terms. That's why I'm very glad to have him today on our campus to discuss the mysteries of dark matter. Where do we come from? Where are we going? What makes up our universe? Hitoshi will address these and more questions in his talk on dark matter and dark energy. Please join me in welcoming Professor Hitoshi Murayama.
Well, thank you, Peter, for a very nice introduction to me. So now I'm under very heavy pressure, being the first speaker of a lecture series, which is advertised to go very long. But if I fail, I may be the last speaker, right? So I'll find out. So this is the poster actually Yohei made about the talk today, the dark side of the universe. And one thing I would like to emphasize that the background image of Andromeda here is actually a result of a major instrumentation we did for Subaru telescope. I'm going to actually talk about that later. So this is the picture of Andromeda. So that will come up later. So the title is The Dark Side of the Universe. But as Peter introduced me, so I have been a faculty member at the University of California, Berkeley for many years. But I also started to work at this Kavli Institute for the Physics and Mathematics of the Universe as its director. So my Berkeley friends didn't like this long title, Director of the Kavli Institute for the Physics and Mathematics of the Universe. Oh, we can remember that. So let's take the beginning and end of the title and shorten it to that. And I hated it. Sounds like a huge responsibility to me. But what we would like to do is really try to understand the universe. So what physicists do is to really ask simple questions, but at the same time very profound, like any kid might like to ask. You know, watching up the beautiful night sky and start wondering, how does this big universe begin? What is its fate? Where we're going? What it's made of? What are its basic laws? And, you know, where do we come from? So my talk today has to do actually with two of these questions: where we are going, what is the fate of the universe, and where do we come from? And of course, these questions have been a realm of religion for many millennia, or maybe philosophy. And only like a bit more than 100 years ago, we started to ask this question in terms of biology, for instance. I'm not really sure if we are evolving the right way these days. But anyway, so this became a scientific question. And to understand these questions and where we come from, where we're going, the machine we'd love to have, of course, is the time machine. Unfortunately, we can't make a time machine. That's against the laws of physics. But we have something that comes close to it. One of them is the big telescope. I'm going to talk about the Subaru telescope later on. And with these big telescopes, with big mirrors, you can collect so much light that you can see very dark objects very far away. And if you look far away, what it means is that you're looking back into the past. Because the light takes so many millions of years to reach us, you're actually looking back into the past. So that's one kind of time machine. Another kind of time machine, which is probably less familiar to you, is called particle accelerators. And what these machines are meant to do is to redo the Big Bang. So the universe started with very small and hot. So with these powerful machines, you can accelerate tiny particles in incredible energy. When you start smashing against each other, you redo the Big Bang. Well, you can't really do the Big Bang, but maybe you can do Little Bang. And that's the way you study what was going on at the beginning of the universe. And just put things on perspective. So this is the same picture of Andromeda you saw on the poster. And Andromeda actually is 2.3 million light years away from us. So what that means is that if there's an alien in Andromeda, pointing their telescope at our planet Earth, what they're going to see us is like this. Because what they see is the way we were 2.3 million years ago. So that's how long it takes for the light to reach our neighbor galaxy, Andromeda. If you look farther, for example, this is a picture of something called cluster of galaxies. This particular one is 2.1 billion light years away from us. And cluster of galaxies means you have about 100 galaxies sort of living together in a tiny village, and that's what this thing is about. So if an alien living there points a telescope at us, what they're going to see is a single-cell organisms. And this is the distant ever galaxy we ever watched in telescopes using Hubble Space Telescope. So starting from this image, you blow it up, blow it further, and this little red smudge is actually a galaxy with something like 100 billion stars in it. And this one is 13.3 billion light years away from us. So if an alien there points a telescope at our planet Earth, what they're going to see? Nothing, because solar system wasn't born then. So that's what I mean. If you look far away, you really look back at the past. And now we know that the age of the universe today is 13.8 billion years. What that means is that if you try very hard to look 13.8 billion light years away from us, then you can see the beginning of the universe. We managed to take the picture of the beginning of the universe. And this was done by a satellite called the Planck satellite launched by European Space Agency. And this is the picture of the Big Bang. And what is shown in colors is, slightly hotter part than colder part that's shown in these colors. But this is actually extremely exaggerated. The temperature contrast is only at 1 part in 100,000. So if you think of, say, 100-meter deep ocean, it's like 1 millimeter ripple on top of it. So it's very, very homogeneous and flat and bland, not very interesting. But nonetheless, this is how we managed to actually even take a picture of the Big Bang. So it really did happen with the Big Bang. Unfortunately, I have to say that this is not exactly the Big Bang, because if you try to look that far back in time, then universe was so small and hot and dense that it's sort of like trying to look into the sun. If you look at the sun, I recommend you don't, but anyway, if you do, then all you see is the surface of the sun, right? Because sun is such a hot, dense ball of gas, the light doesn't go through it, so you can't see what's inside the sun. So the same way, if you try to look 13.8 billion years away from us, then what you see is the surface of the Big Bang. Beyond that surface, universe was so hot and dense, light wouldn't go through it. So unfortunately, we cannot take the picture of the Big Bang, the beginning of the universe. What you see is the surface of it. And of course, when I give a lecture on a Big Bang to the general public, all they think of is usually this Big Bang, and that's not the one I'm talking about. The Big Bang was actually like this. It was a soup of particles. It was so dense and hot, everything was broken apart into tiny pieces. So that's how the universe began. So here's the Big Bang, the very beginning of the universe. 13.8 billion years later, you're thinking about how the universe began. And here is the big soup. And the picture of the Big Bang I have shown you actually came from this point, when the universe was only 380,000 years old. Of course, 380,000 years sounds like a long time for us, but compared to the 13.8 billion years of the lifetime of the universe, this is actually a baby universe. It was just a moment after its birth, and that's the picture we have taken. But of course, when you ask the question where we come from, we really would like to understand what was going on even before then, and that's part of the subject of my talk today, where machines like particle accelerators will come in and play some role. And I told you already that when the universe was so hot and dense, hot means everything moves so fast, so much energy, so even atoms wouldn't exist because pieces of the atom would fly apart from each other. Even atomic nucleus wouldn't exist because each pieces will start to fly apart from each other. So at the beginning of the universe, there were no atoms. There were no nuclei. And only when the universe became about 3 minutes old, universe became cold enough, like a 10 billion degrees Celsius. So it was cold enough then that particles like neutrons and protons start to stick with each other. And that is the formation of the helium nucleus. But we know already that that's about it. So based on this idea, you can actually study universe using machines in laboratory. You can try to throw neutrons against protons each other and see how often they will stick with each other. And then you can make a prediction how much of the helium was made in this big, hot, dense soup at the beginning of the universe. And the prediction is that it should be about 3-to-1 compared to hydrogen. And when you observe the sky and taking data from telescopes, indeed you can see that the helium to hydrogen ratio is about 3-to-1. So that's how we know they were indeed hot, dense soup, and that start to form objects afterwards. None of these things existed at the very beginning. But that begs up actually a new question. So if helium was made in the Big Bang, where do we come from? You need carbon, iron, oxygen, nitrogen, calcium, potassium. You need all kinds of other elements. Where do they come from? So this is a picture of my daughter on a not happy day. And she's made of atoms. And atoms have this nuclei at the center. And as I told you already, they're made of protons and neutrons. And we now know that they're also made up of even smaller pieces called quarks. But in any case, how did proton and neutron get together to form atoms so that we can exist? And the answer turned out to be stars. So this was actually a very age-long question at the end of the 19th century. How does the sun shine? And the answer was not known till Einstein came in and proposed this famous equation, E equals mc squared, which means m, mass, is the same thing as E, energy. So the idea is that at the center of the sun, which is so dense and hot, you can squeeze these tiny protons towards each other, and they become helium in a similar way that happened in the Big Bang itself. And while doing so, you spit out actually a form of antimatter called positron, and the ghostly particles called neutrinos. And the point here is that what you start out with is heavier than what you end up with. And this is crazy, right? If you think of collision of two cars in a big accident, and there was so much debris on the ground, but if you collect them all and weigh that together, that's exactly the mass of two cars you started with. And that's the way we normally think. But here, the mass is lost. And what happened is that the mass then turned into energy. So the sun is shedding its mass to create energy. That's what the sun is doing. As a matter of fact, the sun is getting lighter by 4 million tons every second. Of course, sun is such a heavy object, so 4 million tons is sort of nothing to it. But nonetheless, sun is shedding weight, its mass, so that it can create energy. I tried very hard to shed my mass to create energy. I have not been very successful so far, but that's exactly what the sun is doing. But how do we know that? You know, I told you before, all you can look at is the surface of the sun. That's what's going on inside. It turns out that these ghostly particles called neutrinos are actually very interesting in this context. And there are actually tons of them coming out from the sun. And they are so shy, interact so little, they are not disturbed at all by this entire mass of the sun. They just shoot out with no problems. And so there are actually something like 100 trillion neutrinos going through your body every second. Well, this is a huge number. And even though we are inside a building, then neutrinos would go through this entire slab of concrete very easily. Even during the night when the sun is on the other side of the Earth, they actually pass through the entire planet without any problems. So all these neutrons are sort of shining on you all the time. Does anybody feel this? No? When I ask this question in Berkeley, there's always a couple of people who raise their hand. So people in Okinawa are much more reasonable than Berkeley, I guess. And to really know this is what's going on, one experiment in Japan made a major contribution, and that is called the Super Kamiokande. This is a huge tank of water in underground below 1 kilometer of rock. It's about 40 meters high, 40 meters wide, and it has 50,000 tons of water in it. And you fill up this tank, and each of these round things is like this big, and they're meant to be your eyes to see a tiny flash of light happening inside this water tank. And you can appreciate the size because you see people here on a rubber float. You see them? They are graduate students on a mission. Even though this is a huge tank, you need to make it incredibly clean because if you're trying to see these neutrinos, they interact so little. Any little tiny speck of dust inside would cause other noise, like radioactivity. So you need to keep this entire tank very clean. So what they are doing here on the rubber float is that take a piece of cloth and bottle of alcohol, and wipe it very clean. Go next, and go all the way around 40 meters of diameter. And then somebody fills water a little notch to the next level, start doing the same thing again. Clean. And the whole process takes like 6 months. That's how big the tank is, and you can appreciate the size when I move the picture like that. So using this huge target, once in a while, you manage to see these neutrinos. So this picture is meant to show that the neutrinos are very shy, like ghosts, but once in a while, they cause some reaction in the water tank. And even though you have so many neutrinos coming from the sun, the target is also so huge, you may see maybe 10 of them a day. But like taking a picture of a very dark star and you use a camera, you keep your exposure open for many hours, right? That's how you take a picture of a star. In the same way, they kept the exposure open for 5 years and managed to take a picture of the sun using neutrinos. No light comes in here. In pitch darkness, because it's underground, 1 kilometer rock is above you, but neutrinos do reach this water tank, and that's how you can say the sun is there. So if you happen to be a goblin or something, that's how you know there's a sun, right? And it's not only just a picture of the sun, this is a picture of the center of the sun, because that's where the neutrinos are coming from. So that's how we know stars are factories of building atoms. And here's another example. So this is an explosion of star called supernova. A single star explodes in such a way that becomes brighter than the entire galaxy. And it doesn't happen very often. It happens like once a century or something. But it does happen, and this happened in a very small, tiny suburb village of a galaxy called Large Magellanic Cloud, and that also produced tons of neutrinos. And the predecessor of the Super Kamiokande was called Kamiokande. It was smaller, but small in this case means 1,000 tons. And they actually managed to see these neutrinos after traveling 160,000 light years away. And as I told you already, the neutrinos don't interact very much. So most of the time, the only thing you see is the noise. This is the noise. But for an instant, there was a burst of neutrinos. Even this burst is only 11 neutrinos, but nonetheless, it was a burst nonetheless. So something explosive must have happened. And lo and behold, when people took the telescope and looked at the sky, there was an explosion of a star. And that was a Nobel Prize worth work to Professor Kashiba at the University of Tokyo. And this is an amazing, amazing discovery. Because, you have to fight with this noise. And just a month before this discovery, the noise level was still too high that he probably wouldn't have seen this event. They were still fighting for it. On the other hand, a month after the discovery, Kashiba had a mandatory retirement. So there was only a 2-month window for discovery for something that happens once a century. So something happened exactly 160,000 years before this particular month so that he could get a Nobel Prize. So this is a message to young people here. You need to have tremendous amount of luck to achieve a Nobel Prize quality work. But nonetheless, we learned something very important, namely that even distant stars are also made of atoms down to their cores, and they make atoms. So what we learned from this is that the universe started out with mostly hydrogen. Some of that became helium, as I told you, during the Big Bang itself. So the first stars were made of hydrogen and helium only, no other elements. But those stars start to build bigger and bigger atoms at their cores, and then some of them go kaboom. And if the atoms stayed inside the stars, you wouldn't be here, right? Because you can't take them out to build your body. But because of the supernova, they get sort of stretched out and dispersed into empty space, and so that they become eventually dust. And that dust, again, comes together by the force of gravity and build their children, second generation stars. And again, they start build bigger and bigger atoms inside, and they go kaboom, and spread them out throughout space. So it is believed that our sun is the grandchild of the initial stars. So we are the third generation. That's why when sun was formed, there was enough of these dust made of these heavier elements like carbon, nitrogen, and iron we are made of. And some of these things got stuck together into a little piece of rock called our planet Earth, and that's why you live here today. So if you meet somebody for the first time and they ask you where you come from, you gotta respond, I came from a star. I'm sure they will look very puzzled, but nonetheless, that's true. So my daughter came from that, and Nobel Prize also came from this. So we are all stardust. So that's something we learned. And that brings up the question about the fate of the universe, in this case, fate of the solar system. So even the sun with so massive amount of hydrogen at its core, eventually, it runs out of fuel. It doesn't create energy anymore. Then it cannot support its tremendous weight of itself, so it starts to collapse. But then the outer part of the sun bounces back, and it doesn't quite explode because sun is not a very big star, but bouncing back envelope becomes so big that it is probably would swallow up our planet. that's basically end of life on this planet. Becomes so hot, even if it doesn't get swallowed up, it's so hot and dry. So no life would be sustained beyond that point, which happens in like 4.5 billion years from now. So young people in this audience should be worried about this. So you have to come up with some kind of escape plan. But where do we go to? Well, we used to think that planets exist only in a solar system, but now we know there are many, many planets around probably all stars we can observe in the Milky Way. So this is some statistics from recent data from Kepler satellite, and more than 2,000 candidates have been found. So for any average star, you are bound to find several planets. So they do exist. And using a telescope, Subaru I'm going to mention later, so this is actually a picture of a planet in a different solar system. This is planet. This is also planet. And the star itself is so bright that will sort of outshine everything. So you put a mask where the star is. Even then, you see sort of the lights are smearing out of it. But that way, you can start to look at more dimmer objects around it. And you can take a picture of an extrasolar planet these days. So hopefully, we can find a place to go to. So anyway, so that's what we have learned so far. And so that tells us how the universe was like when it was 3 minutes old. But now comes a story of something we don't really know about, and that's the dark matter. And if we do understand dark matter, hopefully eventually, then we can start looking at the way the universe was like when it was only 10 to the minus 10 seconds old, 1 part in 10 billion seconds. So what is dark matter? Well, one thing we know about force of gravity is that when we go far away, the force becomes weaker. And that's exactly what happened in the solar system. So if you look at the different planets orbiting our sun, the farther out you go, the gravitational pull from the sun becomes weaker. So if you go with the same speed as the planet Earth, then it will start to boom and get out of the solar system. So the outer planets need to go more slowly to stay within the orbit. And that's exactly what happens here. If you go farther out, more slowly the planets move. But now comes the similar question about a galaxy. People used to fight over whether the sun is the center of the universe or the Earth is the center of the universe. And we often learn in school that the sun is the center of the universe at the end of the day. Wrong. Our sun is here. So it's not the center of even our own galaxy. It's 28,000 light years away from the center. So what that means is that our sun, our solar system as a whole, is actually moving around inside a galaxy. So we revolve. And in our galaxy, there's something like 100 billion stars. And within it, our sun is just an ordinary average star. And it's moving at a speed of about 220 kilometers per second. That makes you sort of dizzy, right? So how long does it take to go to Tokyo with this kind of speed? Maybe 10 seconds? No, we are moving incredibly fast. And of course, you would say, okay, because there's so many stars in a galaxy, their gravitational pull must be keeping us inside the galaxy. But the stars are something you can observe with telescopes. You can count them up. Is there enough gravity? No. So if you think the galaxy is made up only of stars, we should have gotten out of the Milky Way galaxy many tens of billions of years ago. But we're still in here. So what's going on? So that means that something else is pulling us. Not just the stars, but something else. As a matter of fact, this is the data. Even if you go farther and farther out in the galaxy, none of the stars will slow down. That's ridiculous, right? That's against what we learned from school. That's again doesn't look like data from the solar system, but that's the real data from the measurements. Nothing slows down, even if you go farther out. And the only explanation is that if you go farther and farther out, there is actually even more and more mass that's pulling us towards the center of the galaxy. So there's something that pulls you into the center of the galaxy, and there's some kind of matter there. But we don't see it in telescope. That's why we call that dark matter. We don't see it. That's why dark. But it's matter because it produces gravitational pull. So we know there are dark matter in a galaxy. And not just ours. Against Andromeda and a whole bunch of other galaxies you can study. In basically all of them, as long as you can measure them, it doesn't slow down if you go farther and farther out. And so that's one of the reasons why we believe there is something called dark matter. And here's another reason. This is actually a real picture from the telescope, but doesn't it look kind of cute? You know, you see two eyes, and nose, and mouth, the frame of a face. And this system is so cute that it got actually a nickname. It's called Cheshire Cat, like Alice in the Wonderland. And strange thing is this. You know, what is this thing here? You know, this obviously is a galaxy. This one is too. This one is a galaxy too. But what is this object that looks so much stretched out? I told you that stars are moving, right? If there were such a stretched out object, the individual stars move so randomly that they would disperse right away. So this kind of object wouldn't exist very long. But we see them a lot in our universe. And also in this picture, so this is again a cluster of galaxies, 2.1 billion light years away from us. Again, these round, beautiful objects are galaxies, so that's fine. But then you start to, your eyes start to get attracted to something like this. So very long, stretched out object here, also here, also here. Here's another one. There's another one here too. You know, what are they? Well, this is a trick dark matter is playing on you. So what's going on here is this. So here's the cluster of galaxies, and there's actually a lot of dark matter in it. So there's a big mass. And if you look at the galaxy which is behind that sea of dark matter, then the light coming from this galaxy gets pulled by the gravitational pull and bends. So on its way from this faraway galaxy to a telescope, light gets bent. So this collection of dark matter acts like a magnifying glass. And I'm sure you have an experience. If you look at the very edge of magnifying glass, everything looks very, very distorted and stretched out. And that's exactly what's going on here. So if I actually put this in a computer simulation, just imagine that you have a bunch of galaxies in the background flowing like a river and pass behind this cluster of galaxies. Then what happens is that these things start to get stretched out like this. But once they pass away, they return back to the original shapes because nothing happened to them. They are at completely different locations. So it's just a trick played by dark matter in front of them, and nothing actually happened to those galaxies. So this is actually wonderful because if you see tricks played by dark matter, then you know where the tricksters are. Namely, you can tell how much of this thing is where. For example, this is a typical image, again from Subaru telescope. And these shiny objects up front that look like crosses are just nearby stars, so please forget about them. Just focus on these tiny little dots in the background. And each of these tiny little dots is its own galaxy with like 100 billion stars each. And if you look closely at them, with a modern technology, you can tell that their shapes are not quite right. They are distorted. And so the dark matter is playing tricks on us. So that allows us to take make a map of dark matter like this. So we know exactly where they are, how much they are, and that's how we learned that more than 80% of matter in the universe is not atoms, but something different, dark matter. I vividly remember learning in elementary school that everything is made of atoms. That was a big fat lie. So we have to rewrite the textbook. And we became sure of this only in 2003. So it's not had been known for a long time. And the fact that we know dark matter is not atoms is, for example, from this picture here. This looks like a beautiful picture from a telescope. But this is actually a very ugly place that you should be happy that you're not there. So what's shown here in pink is the ordinary gas made mostly of hydrogen and helium. And they became so hot that it's radiating X-ray. So that's this picture in pink. What's shown in blue is where dark matter is, because again, they are playing tricks on us, then you know where they are, and this is where dark matter is. So you see two pairs of dark matter and gas, and dark matter and gas. So each pair is a cluster of galaxies of its own. But here comes the problem, right? I told you already that dark matter is keeping things together by the gravitational pull. But somehow, this gas is not together with dark matter. This gas is not together with dark matter. So what happened? So the way we understand it now is that this is an aftermath of collision of two clusters of galaxies at a speed of 4,500 kilometers per second. The entire Japanese the peninsula in about a second. So it's that kind of speed. And when two cluster of galaxies collide at this incredible speed, what happens is this. So each cluster of galaxies is basically just made of dark matter with gas a little sprinkled in at the center. But when they collide, gas made of atoms would scatter against each other. They mingle with each other, they become hot, and there's a friction, they slow down. But the dark matter keeps moving as if nothing has happened. And then the gravitational pull from dark matter sort of drags the ordinary gas behind it. And that's how we can explain this picture. So what you learn from this is, first of all, cluster of galaxies is basically just made of dark matter. That's the main component. But second, when they collide, atoms do scatter against each other. They interact. But dark matter doesn't seem to interact with atoms. Dark matter doesn't seem to interact with dark matter itself. So they're kind of spooky objects. So they don't interact with anything, it seems to me. So that's why the poster shows this spooky picture. But it's important to know that the dark matter is not evil. Dark matter is actually your mother. What I mean by this is that, this is a computer simulation, but I told you we managed to take the picture of the Big Bang. So we know how the universe began. And there was slightly hotter parts and slightly colder parts, I told you. And slightly hotter parts have a little bit more dark matter in it. And by gravitational pull, that pulls more stuff into it. Then it becomes more dense, more gravity, pulls more stuff in, and eventually starts to develop this contrast between dense spots and sparse spots. And in the dense spots, the gravities become so big that it pulls in the ordinary gas, and they interact with each other, as you show on a previous slide, and they emit light, become colder, and condensed, and become stars in galaxies, and you. That's how you were born. But in a hypothetical wrong universe without dark matter, even 13.8 billion years later, nothing. There's not enough gravitational pull to bring stuff together to form stars and galaxies, so hence no you. So that's what I meant, that dark matter is your mom. She formed us. But nobody has met her yet. So we got sort of separated at birth. So then you have to work on this, right? You would like to meet her and thank her, and that she's the reason why you exist, but nobody has met her yet. So that's where we are. And one of my colleagues, George Smoot, is a Nobel laureate. That he's the person who took the picture of the Big Bang for the first time. It's not as good as the picture I've shown you, but he was nonetheless the first person to take a picture of the Big Bang. And after he got the Nobel Prize, he was asked by the university administration to do something interesting with his students, and he said, no, I'm going to use what's called a cow band. It's a marching band for football games. So this is what he did.
I really admired the band, and so when they said we wanted to react to the Big Bang with the guys from your lab, I said, no way, I want the band. Okay, so now I got to tell you what the Big Bang is so you guys can do this before the sun goes down. Okay, so the idea is everything in the early universe was packed together very densely. It may have gone for infinite. We don't have infinite people, so we just have to use what we got. And everything stretched, right? Everything got bigger. And the further away you are, the faster you go. So we're going to want to start at the beginning with everybody packed dense and jostling around and playing high tempo rapid. 1, 2, 3. Then at the mark,
this is the Big Bang.
Everybody moves apart. The people on the outside moving faster than the people on the inside. And there's a little bit of irregular motion, so miss some steps. Okay? I know you can do this. Right? And then what happens is you're going to coalesce together in groups of 6. Right? So you have to find 6 buddies. And half of you are going to form spiral galaxies. 3 people facing one way, 3 the other, and you rotate slowly as you move out. And the other half form elliptical galaxies, which are round blobs that keep moving out.
It's a spiral galaxy.
Now, There's a brass section out there called tubas. They make a really spectacular spiral galaxies, a really big one, like our own galaxy or like Andromeda. So you guys get to be near the middle, and you get to make a really cool, you don't have to run out so fast, but you get to be able to orient where half is facing the other way, and you get to rotate with a sort of twist up. And you're like the centerpiece of this whole thing. Go tubas. Great, guys.
And you need to remember, 80% of people there is dark matter. You don't see them. And George is at the center of a Milky Way galaxy, which means he's a supermassive black hole. You don't see him either. He weighs as much as 4 million times the sun. So most stuff in the universe you don't see. But that's how the universe is like, and we have learned that. So I kept telling you about Subaru telescope, which has been giving us a lot of interesting data, and this is how it looks. It sits atop the Mauna Kea on the big island of Hawaii. Recently, it has been having problems with eruptions and earthquake, but it's a super telescope. And when you hear the word Subaru telescope, you might be misled that it's about a car, but it's not. And what Subaru actually means that if you closely look at the emblem of a Subaru cars, this is actually a picture of the stars. So the word Subaru is just a word, not about a car company, but it's about a star cluster called Pleiades. This is a Japanese name for this Pleiades star cluster, and hence Subaru. And the reason why this telescope is so good is it's among the biggest telescopes in the world. The size of the mirror is 8.2 meters. And so, but among those big telescopes, Subaru has the biggest field of view. So it can observe many, many more things than any other telescopes can do. And to exploit this large field of view, we started this institute, Kavli Institute for Physics and Mathematics of the Universe, we started to build a new digital camera for it. But it's not like a digital camera you might have in your cell phone. Just the mirrors, the lens itself is this big. And if you put that into the entire camera, it's actually 3 meters tall, and it weighs 3 tons. So you can't carry that around, really. And this got mounted on this Subaru telescope with this wide field of view and also good depth because you can see so far away. So we recently put out this world's largest 3D map of dark matter. So this is the more recent universe that's nearby. This is far away. That shows the past universe. And this is a big area of the sky. And this is how dark matter is distributed in a 3-dimensional fashion. Now we can do things like this. So we know they are there. And also, this tells you that the dark matter is our mom, because if you look far away, the contrast is not as big as more recent universe. So dark matter starts to clump together. And if you compare that to the distribution of galaxies, you see they are very correlated. So namely, where dark matter is, you're bound to find galaxies. So that's how galaxies are born. So that's why I'm telling you, she is really your mom. So you would like to meet her. But who is she? And of course, we don't know yet. So we have some ideas. And one of the ideas called WIMPs, the dark matter is a WIMP. It's sort of the monster version of neutrinos. They go through their planet with any problems all the time. WIMP is actually an acronym, which stands for Weakly Interacting Massive Particles. So idea here is that this is a heavy elementary particle, like electron and top quark and so on. And this was born in this very hot, dense soup of the universe at the beginning. And they got left out a little bit. And that's what this dark matter is actually about. So if you think of this dark matter to be a very shy particle, we've been there before, right? We managed to see neutrinos. It's kind of like that. So the people started to mount experiments again underground. I also used to work underground myself. This is when I actually brought my picture and friends into this underground Kamioka site. And the experiments are way down there on this tunnel. And you see huge cavities dug out of this underground location and build instruments. And one of them is called XMASS. So the idea is that if you build big, very sensitive instrument placed underground in a very quiet environment, maybe you can see this little clink of dark matter caused by the clink of dark matter scattering of the ordinary stuff in your experiment. And I apologize, the next video clip is actually in Japanese, but you get the idea.
ス
So
ー
this
パ
is
ー
the
神岡
underground
間での
tunnel.
あ
Maybe you
る
can
神
bring the
岡
volume
鉱山
down a
の
little
地下
bit.
です。
And at the end
こ
of
こ
this
には
tunnel,
も
you
う
find
一つ
Super
別に
Kamiokande,
ダーク
but
マター
also
の観
another
測施設
cavity
がありま
where
す。
you find an experiment that looks for dark matter. So this is
ダーク
one.
マター観測
In
装
this
置
water tank,
X
there's a
マス
smaller
です
vessel filled with liquid xenon, and that is designed to listen to the small clink of dark matter scattering inside this detector. So that's something that's going on. But other people are not as patient. So even if you build a big device like a X-mass, which has a 1 ton of liquid xenon, we already know that the dark matter wouldn't cause any reactions, maybe at best once a year. See, you have to be very patient. Most of the time, you are just surrounded by a huge amount of noise, and you need to make sure that you don't miss the little clink happening once a year. And some people are not as patient as that. So they started to say, okay, well, Big Bang made dark matter. Maybe we can do that too. And that's the idea of the particle accelerator. I'm sure you have heard of this humongous experiment called Large Hadron Collider at CERN laboratory in Europe. And this dotted line is the border between Switzerland and France. So if you go there, you see a dotted line on the ground, right? And here's the airport of Geneva. And this is how big that tunnel is. It's 27 kilometers in circumference, much bigger than the runway on the airport. And this entire stretch of 27 kilometers is fitted with the high-tech devices all the way through. But the idea is very simple. So you fly protons that make up a nucleus round and round many, many, many times, and they get sped up, and eventually you go boom. And that is meant to basically redo the Big Bang or maybe Little Bang. So it's sort of like a hammer throw. And this is how the tunnel looks inside. So these are all high-tech equipment. The temperature inside is even colder than empty space out in the universe. And you can barely see the tunnel is round because it's so big. It looks almost straight. Of course, particle accelerator doesn't sound very familiar to many people, but you actually find many of them at hospitals because they're being used for cancer therapy, cancer diagnosis, and so on and so forth. So it's actually not a very rare object. There are some 2,000 of them in Japan, and many tens of thousands in the entire world. It's just a bigger one of this. It's the Large Hadron Collider. So can we really make dark matter? Of course, we don't know yet, but the idea is pretty simple. So the proton is not a very particularly heavy object. So it's sort of like a tricycle. Another tricycle. And then what do? You pedal like crazy and you speed up the tricycles to an incredible speed with energy, and then you smash them against each other. And then comes the equal MC squared again. So this energy of tricycles can turn into mass. So from the collision of tricycles, you might see an airplane in tanks. And that's the idea of particle accelerator. And we know that works. And if this tank happens to be dark matter, you don't see it. But you can tell it's there because there's an airplane on the other side. When you smash things against each other, everything needs to be balanced. If you see something big over here, there gotta be something big also over here. But then the fact you don't see it means you managed to make something invisible. And that's how we look for dark matter. Again, unfortunately, we haven't managed to actually see dark matter this way yet, but at least that's the idea. So this is an experiment a Japanese group is involved in called ATLAS. And do you see pictures of people? And this is, again, a huge collection of high-tech equipment that are 22 meters high, 40 meters long. It's basically a super Kamiokande put sideways. And you need that kind of humongous object to see everything that spurns out from this incredible collision of two tricycles. So that's the idea. And they've been very also active in outreach, so they created this video clip even when they're still building it. So protons coming from both sides, they smash against each other, that produce tons of other stuff, and this huge device is meant to collect them all. Now you can tell which movie they had in mind. And they are dead serious people. Keep watching. And this is a picture during the construction of it. Again, you see a person here. And this whole thing is very, very big. And this inner part of this is now filled with high-tech devices, and that's how you detect everything that comes out of this big collision. And as I told you already, we haven't discovered dark matter yet, but this search is still going on. So if you do understand what dark matter is, if you manage to meet her at the end of the day, then we start to tell how the universe was like when she was born. And that means we can see back towards the beginning of the universe this close, 1 part in 10 billion seconds. So that's how we like to know where we come from. Now, after telling you where we came from, you came from stars, but stars came from dark matter. Now we start to ask the question, what happens next? Where do we go next? And that has to do with another mysterious material called dark energy, and that holds the key of the fate of the universe. So thinking about the expansion of the universe as a whole, that already sounds very mind-boggling and sounds crazy. But according to Einstein, it's just a simple force of gravity. So the idea is again, very simple. So everything starts with this big bang. Everything starts to spread out. But the force of gravity pulls, so that puts brake on the way that everything sort of spreads out. So eventually it should just slow down. So the way we used to think for many, many years is that when the universe started with this big bang, initial momentum is what keeps the universe expanding, but this should be slowing down, right? So it should be slowing down. So the universe should behave this way. And if it slows down to the extent that it stops at some point, it starts to come back down, then the universe might end up in a big crunch, we call it, the big crunch. You may actually see the universe just coming to a collapse down to a point. Or maybe, if the initial momentum is big enough, maybe it just escaped the force of gravity and just keeps expanding forever. So people wanted to know which is the right fate of the universe. And you started to measure how much universe is slowing down so that we can tell maybe we're going back to a big crunch, or maybe we just keep expanding forever. But when people really try to measure this, again, the idea is simple. If you do the measurement of how universe is expanding nearby, that's a recent expansion. If you measure how universe is expanding far away, that's the expansion in the past. So by comparing far away expansion, that's in the past, and nearby expansion, that's more recent, you can tell how universe is slowing down, and hence the fate of the universe. So people start to measure that, and then came a huge surprise. It wasn't slowing down. It's speeding up. That's really crazy. I told you that the gravity only pulls, right? It should put a brake on expansion of the universe. But it's speeding up. Something is pushing the universe. It's not gravity. Gravity only pulls. Something else is there that's pushing the expansion of the universe. And we don't know what this is either. But this discovery is now so established that it's already awarded by Nobel Prize. It's one of my Berkeley colleagues called Perlmutter. So at least we learned something. You know, there's something that's pushing the expansion of the universe. And so it's some form of energy. So we call that dark energy. So it's dark, again, because we don't see it in telescopes. But it's energy because it's capable of pushing the expansion of the universe, hence dark energy. And I think it's fair to say that this is probably the biggest mystery in modern physics. Nobody understands this. And if the expansion is speeding up, maybe it comes to the point that universe becomes infinitely fast. Then everything gets infinitely spread out and ripped apart. Universe may end there. And that possibility is called the big rip. Universe gets completely ripped apart and universe ends at that moment. So the discussion of the fate of the universe now totally changed. Do we keep expanding forever? Or would the universe end by infinitely ripped apart from each other? And I'm sure you are very confused now because I talked about dark matter and dark energy, but they are very different things. First of all, atoms, we thought everything is made of, actually make up only 5% of the universe today. And when the universe becomes twice as big, volume becomes 8 times bigger, and atoms, of course, will thin out 8 times. That's the ordinary behavior of matter. Dark matter makes up about 27% of the universe today. Even though we don't know what it is, at least it's matter, so when the universe becomes bigger, it does thin out, the same way the atoms do. But dark energy is different. First of all, it makes us 68% of the universe today. That's the biggest component of universe today. And when universe becomes twice as big, volume becomes 8 times bigger, it looks as if it becomes 8 times bigger. It's an infinite source of energy. It just keeps wearing out. And so that's how it manages to push the expansion, because it keeps multiplying. But with the current data, we don't quite know if this is really 8 times or maybe 7 times. Then dark energy is losing its momentum. Maybe the universe would start to slow down again. But if it's 9 times instead, dark energy is picking up more and more momentum, so that's what would lead to the big rip. So we need to do a much better measurement to tell if it's really 8 or maybe 7 or 9, and that's how we think we can tell the fate of the universe, and that's what we like to do. And when I told this idea of big rip to the NHK broadcasters, they actually decided to make a TV show out of it. And again, I apologize that the narration is Japanese, but this is their visualization of Big Rip. So this is about 200 million years before the Big Rip. And because the dark energy is stretching the entire universe, then everything starts to sort of move away from each other, and even the galaxy can't stay together. So dark matter is pulling us, but dark energy is stretching us, and eventually dark energy wins, and then the galaxy would not stay together. And when it comes even closer to the Big Rip, this is something like a few hours before the Big Rip. Even stuff inside the star starts to get stretched away from each other, and the star would just completely disappear. And I warned the NHK broadcasters that there is no air in space. You shouldn't be able to hear any sound, but they put this booming sound in the video. It's wrong, but anyway. And when it comes to really, really close to Big Rip, nothing can stay together. So everything gets now ripped apart into smaller and smaller pieces down to the elementary particles, and becomes infinitely thin, and everything gets spread out from by infinite distance, and that's how the universe might end. So universe started with the thick soup of elementary particles. It may end up with very thin soup of elementary particles. Maybe that's the way it happens. So this does, in this case, looks really evil. And one thing we do know, though, is that these beautiful pictures of galaxies we can take together with Subaru telescope and other telescopes, and these galaxies are moving faster and faster away from us, right? So eventually, we would lose sight of them. So kind of observations we can do with telescope and study far-away galaxies and ask the questions where we come from, where we're going, we can do this only now. So I've been telling the funding agency that we need funding right away that we can observe the universe. So to really understand what's going on here, what we basically need to do is to do a census. If you ask the question, what's the future of this country looks like, you do a census and you discover that it's quickly aging. The similar picture for the United States was a little healthier, but this is mostly due to the immigration. So we really shouldn't stop immigration in the United States, by the way. But anyway, so this is how we can project the future, right? So we need to do also a similar thing about the universe. We need to do the census of the universe, which means you need to observe just tons of things so that you can start looking at the statistics of them, and then that would allow us to tell the future of the universe. And so that's the project we're doing. It's called SUMIRE, the Subaru measurements of images, namely with digital cameras, and redshifts using a spectroscopy. So I told you already that Subaru is one of the largest telescopes, has a very large field of view that you can quickly capture many objects at once. And if you'd like to do a similar thing on Hubble Space Telescope, that's probably the most famous telescope in the world, it would take thousands of years. So I don't recommend that to the graduate students here. But with Subaru, the field of view is about 1,000 times bigger. So you're in business in a couple of years. Anybody interested? So the idea is that we built this digital camera. We're already conducting a large survey for 300 nights. And that would allow us to capture something like 300 million galaxy images, and using this incredible power of having nearly 1 billion pixels of the camera. And we are now building the next generation instrument. It's a spectrograph to measure the color. so that you can tell how quickly the galaxies are speeding away from you. So that requires a very good measurement of colors of the objects. So that is called the prime focus spectrograph. But again, if you're looking at the color of individual galaxies, you again need to spend thousands of years doing so. So the idea is that you bring in a bundle of 2,400 fiber optical cables. You put that at the tip of a little robot. Each robot actually sort of points each optical fiber cable towards a particular galaxy you would like to study. But you can take a spectra of 2,400 galaxies at once. And that's the instrument we're building right now. It's a very complex project. It has many, many different components, but many of them are being readied. And this is the little robots I mentioned that actually points the optical fiber cable to a particular direction. We call them cobblers. And this is one a video that shows how it can move these optical fiber cables around and point them with an accuracy of 10 microns in less than a minute. And that we developed with NASA JPL. So we started with a smaller collaboration with Princeton and a National Astronomical Observatory Japan and Institute in Taiwan. Now it's growing to much bigger collaboration these days because the instrument actually costs about $80 million. And we are still short by a couple millions. So I created a promotion video. So here we go. So idea is that you're looking at these faraway galaxies and ask the question, how did the universe begin? And the question of dark energy is, does it have an end? We also would like to understand how our stars and galaxies have been assembled. So that's why do we exist? And the fact that we can do this is really amazing. You're looking at this galaxy many billions of light years away from us, and individual particles of light, photons, get spread out in all directions, but some of them manage to reach our galaxy, reach our solar system, pass through all these planets, find the planet Earth, find this big island of Hawaii, and eventually find their way into this telescope. That's why you need a big telescope to maximize the possibilities and get bounced around by this big mirror and get into this individual optical fiber cables, and they get routed towards the next room, which has the spectrograph that spreads the light into all colors and wavelengths, all the way from near infrared to blue. So that's how you can see individual lines, and that tells you how what the galaxy is made of and how quickly it's moving away from it. So that's what we are trying to do now, and you can see that this instrument really rocks, right? So right after I finish up my talk, I'm going to pass out the hat so that I can collect some money from you. So anyway, so I talked about these two mysteries about the universe, what is fate and where do you come from. They are very simple questions, but I hope you appreciate that it's a very, very profound questions. But surprisingly, they are scientifically accessible questions. That's where exactly the excitement is. So what we are doing is really this. Thank you for your attention.
Well, Hitoshi, thank you for a wonderful seminar, equally informative and entertaining. And I'm sure you will entertain a few questions.
I'm sure I can do that. Don't be shy.
Here we go. Right there, the blue T-shirt.
I think I don't need a microphone. You showed a very nice picture, like creation of galaxies in the presence of dark matter and without the presence of dark matter. So it was like after 2003, but probably physicists, they also thought about this problem before.
Yeah, that's right. So what happened?
How did they explain without?
Oh, yeah. So, scientists actually tend to be a conservative people, right? So if you think that there's something out there you don't see, normally you would think that, okay, they may be just stars that happen to be very dark and dim. And people try that idea. But even dim stars, there are ways of looking for them. So one of the ideas is keep observing millions of stars in this large imaginary cloud. But if that dim star happens to pass through the line of sight towards one of the stars, then again, it acts like a magnifying glass. So that star should look brighter for the moment. And people look for it, and we also did that with the Subaru telescope. No sign of it. So it's not dim stars. Maybe neutrinos, because they are also very shy particles. But even that didn't work out, because neutrinos are too light. And that's another Nobel laureate, Kajita, who discovered the neutrinos have tiny, tiny mass, and that mass is not big enough to explain dark matter. So basically, we tried everything we knew of, which might act like dark matter, and we completely failed. And so that's what happened in 2003. We tried everything, and none of them worked, and we learned that. So we knew dark matter does exist for a long time, but we didn't know till 2003 that it's none of the things we know.
So you showed this picture of the matter getting diluted and the dark energy being augmented by a spectroscopy. Just wondering, how does this is compatible with conservation of energy?
That's a very good question. There are two ways of answering this.
Must be a physicist.
The first way is that energy is not conserved. It's not. And if you think of these, the light coming from this Big Bang itself, it started out with the kind of light we can observe, but it's now become a radio wave. Because as the universe expanded, the wave of light itself got stretched. And a longer wavelength light means the radio. And the photon, the particle of light of radio, is much smaller compared to the energy of the light with the kind of wavelength we can observe. So each photon kept losing energy as it travels through space. Energy is lost in that case. If energy can be lost, it can also be gained. And the reason why energy doesn't need to be conserved is that this is actually a mathematical theorem due to Emilie Noether, it's a female mathematician at the beginning of the 20th century. She has shown that in order for energy to be conserved, you need an assumption. Any theorem requires an assumption. The assumption is that there's no beginning of time. If everything stays the same, the energy should be conserved. But universe had a beginning. So according to her theorem, energy doesn't need to be conserved. It can be lost. It can also be gained.
What hopes do you have from gravitational wave astronomy in terms of meeting your mother?
One of the things we learned is from gravitational wave is also an interesting question. Where does this come from? Gold, platinum, silver, all these precious metals. And what you can make in stars is only up to iron. We know that because if you try to squeeze things together to build bigger and bigger atoms, beyond some point, you need to put more energy to form these atoms. So that's basically iron nickel. So you can actually build bigger atoms than iron nickel inside the stars. You need much more violent environment where bigger atoms like gold and silver can be made. And the last year we learned where. That's where you have the supernovae that goes kaboom, and there's a core of the star that becomes left over. It's called a neutron star, where the entire mass of the sun gets squeezed down to about a few kilometers. It's an incredibly dense object. And it's built practically only of neutrons and no protons and electrons. And in some cases, the neutron stars may be just circling around each other. And as they circle around each other, they sort of start to wobble the universe. It's sort of like imagining the two balls on a sheet of a bed. Then you start to form these ripples and whirls and so on. So it's like this. So that's the gravitational waves. That's the wobbling space and time. And then because it's emitting gravitational wave, it loses energy. Eventually it starts to circle faster and faster and closer and closer, and they merge and to form a big black hole. But when they merge, before becoming a black hole, you have so many neutrons there, and that's where you can build bigger atoms, and that's where